truc d'élite, là.
Non, c'est pas dans le jet set. Ou le jet set est rendu bien bas, en tout cas.
J'attends le site de l'Ornet, hein, parce qu'il y a un gars qui doit venir, on attend qu'il me met devant. On m'a dit qu'elle vient ça.
Robert, tu connais Sébastien Paquet, ces gens-là? C'est un nouveau prof, là.
Ici?
Ouais.
Quel
Champ d'informatique. On est rendu 4 en informatique. Si je comprends. C'est ça.
Tu travailles dans?
Je travaille dans le site, dans le web social. Les blogs, les wikis, les outils collaboratifs. Ouais, j'ai fait ma thèse dans ce domaine-là. Ça, puis les partages d'analyse. Et puis je fais des recherches là-dessus. Là, j'entends faire un cours là-dessus. C'est ma première expérience de préparation de cours en ligne.
Ouais.
On nous montre des cours de l'université.
C'est ça.
J'ai eu mon cours, mais à distance.
Tu peux toujours jamais te présenter en classe. Viens jamais en classe. Ça veut pas dire que c'est bien bon.
Il y a des gars qui se font semblant en classe. En général, ça aide. Même quand j'étais étudiant, qu'il n'y avait pas de formation à distance, on faisait la formation à distance, on en envoyait un au cours d'introduction pour vérifier les bibliographies, puis voir ce que le prof avait dit, puis après on se divisait les bibliographies, puis on s'en allait à les bibliothèques où on était, on faisait les travaux, puis on envoyait ça pour se présenter aux examens.
Dans le fond, un cours de maîtrise. Les gens sont supposés être assez autonomes pour apprendre par eux-mêmes.
Oui, on espère.
Idéalement, même les étudiants qui ont fait quelques années au bac devraient être.
Troisième année du bac.
Si tu finis avec un bac et tu n'es pas autonome, il y a quelque chose qui ne marche pas quelque part.
Oui, c'est ça.
Il faut que ton patron soit là. Bon, aujourd'hui, tu fais ça. Bon, demain, tu vas voir ça.
Il y en a qui ont besoin de.
C'est tough for one. Waiting.
L'enthousiasme. Pour les motiver.
Qu'est-ce que tu fais quand le prof n'est pas un gars enthousiaste?
Ben là, finalement, t'es mieux avec un cours à distance.
Parce que, tu sais, les profs ne sont pas tous enthousiastes.
Ben non, je sais.
Non.
Non, mais c'est ça. C'est toutes sortes de
Ceux qui ne peuvent pas exprimer non plus leur paternité ou leur maternité, puis sont obligés de paterner les étudiants. En fait.
C'est ça.
Parce qu'il y a deux côtés, hein, les étudiants pas autonomes, mais il y a ceux qui ne rendent pas autonomes.
Il y en a qui aiment ça.
Ah oui.
Compensation. Parce qu'il n'y a pas assez de maternelle à la maison.
Seconde vocation.
Il y en a, ouais, c'est ça. Il y en a qui traitent des enfants aussi comme des étudiants comme des enfants.
Et d'autres qui traitent des étudiants comme des enfants comme des gradués.
Ouais. Moi, j'ai tendance à faire l'hypothèse qu'ils sont autonomes.
Ouais. Ah oui, c'est ça qu'il faut faire. C'est ça qu'il faut faire comme hypothèse. En cours de route, finalement, les faiblesses se manifestent.
Ouais. Mes étudiants, moi, qui ne sont pas très autonomes, ils ont tendance à prendre beaucoup de temps. Je les pousse pas.
Mais c'est ça, il faut les ramasser à un moment donné pour leur donner des échéances.
Non, mais moi, je ne suis pas le genre, c'est ça. Mais s'ils sont pas assez grands pour faire le travail, ben tant pis pour eux.
Dans mon cours de recherche d'information, il y a plein de vos étudiants qui arrivent.
J'ai entendu parler.
La première question, c'est quand est-ce qu'elle s'est due?
Le diffusion.
Ouais,
J'ai entendu parler, ben oui, c'est ça. Yvan et Matadini, qui est notre directeur, disait qu'il y a des étudiants qui ont dit que c'était un des examens les plus difficiles qu'il y avait eu. Au bac.
Non, c'est vrai.
Puis là, non, mais c'est ça. Ton style ou bon, tu fais certaines connaissances mathématiques.
Oui, mais j'ai pas d'échec. J'ai aucun échec.
C'est vrai, ça c'est bien
Aucun échec. Il y a des étudiants qui ont lâché, par exemple.
OK.
Ouais.
C'est ça. Mais tous ceux qui sont rendus jusqu'au bout, je pense que la plupart, c'est tous qui ont fait l'échec, même pas de D.
Excellent.
Il y a beaucoup de A.
Ouais. Ça fait que ça.
Tu sais, la perception des étudiants, c'est toujours.
Ouais.
OK, Daniel, comme c'est pas toi qui fais la conférence, tu vas peut-être présenter Hazel. Ouais, on va commencer parce que je sais qu'il y a des gens qui doivent venir de leur net, mais s'ils décalent de 15-20 minutes, ça va être trop difficile pour Hazel.
Hazel will collapse on the ground.
Bad, est-ce que c'est.
Okay, so so Hazel is working on. How should I present her? So Hazel has been working on her Ph.D. for about a year now.
Yes.
And this talk is a follow-up on a presentation she did this summer at IEC Soft. And basically, she's working in the area of data warehousing, and the general idea, as illustrated by the title, is to find interesting subsets in large data sets. And what is interesting? Well, Hazel will tell us what is interesting.
Oh, okay. Thank you. Thank you for coming today. The outline of my talk today, first of all, I will talk about motivation for data warehousing in general and the motivation for our work in particular. Do a review of OLAP operators that are currently available in commercial data warehousing software, and then present our new proposed operator, the Diamond Dice, talk a little bit about some definitions associated with it and some of the properties that we've established for our Diamond Cube. And then talk about some of the early experiments that we have done on a real-world terrorism data set, and finish up with a summary of where this work is probably going. So to begin with, if we let's talk about databases generally. Suppose we have a car dealership, perhaps. We would most certainly store all our information in a relational database system, all our information about sales, inventory, employees, that kind of thing. And a typical query that I might run against that database might be to find the price of a particular vehicle that we have already sold. So the SQL that I would run or execute would be select the price from the sales where some limiting description would identify the unique vehicle that we're looking for. Very straightforward query. Relational database management systems are optimized to execute that kind of query very efficiently and very quickly. If, however, I am a business manager and I'm more interested in the overall performance of my company, and I want to answer some big picture questions. And again, our car sales company is what the example is from. Perhaps we had a marketing campaign that ran for maybe 10 days, and it was targeted at a particular vehicle, and I want to establish how well this marketing campaign worked. I might ask a query something like this: find me the total sales of Camry, the vehicle that we had targeted over this 10 days period, and compare the sales by dealer. I want to know which of my salespeople did the best work as a result of this marketing campaign. And here, those of you that are familiar with SQL might recognize, even if you're not familiar with SQL, you can see that this particular query is much more complex than the first one that I presented. And if we look at the from here, we're touching at least three relations, or three tables, which could be very, very large. We could potentially, with this query, be touching every tuple in our database. And we're doing a lot of calculating. We're doing an aggregate operation here where we're adding up all the total sales, and we're filtering out the model, and we're filtering out the dates, and we're doing a lot of work here. And this SQL will work, it will execute, and it will return the result that we're after assuming that our database is set up with those particular tables and fields. However, if I'm a business analyst or a manager, I probably don't want to sit and wait for a few minutes for this query to finish executing. I want the answer to this kind of query presented to me in constant or near constant time. I don't have time to waste waiting while a relational database management system churns and calculates this kind of result. So, having said that, a few years ago, a structure or was proposed called a data cube. So the idea is that we take our transactional data from our regular database and transform it into a cube. So now elements that were values sitting inside our table, like the dates of when sales happened or the models of vehicles that were sold, now become dimensions in our data cube. And associated with these dimensions, we have measure values, which could be, as in our previous example, the sum of sales, or they could be average or maximum or minimum. Other measure values could be associated with them. So as we see, a data cube is inherently multidimensional. Here we have a cube in 3 dimensions, but typically they run to many more than 3 dimensions. They provide a summary of transactions, because all these, the measure values here would be pre-computed. This thing is done offline, and then the structure is created such that it can provide quick answers to the queries like that previous complicated one that I showed you. And the other thing to notice about data cubes is that they are typically large and very sparse. There are a lot of potential cells in this cube that are empty and will remain empty, whereas there are only a few that are actually allocated and have values in them. So one motivation for this work and for work generally with data warehousing is how do we reduce the amount of storage required, or how do we more efficiently store this information. Data cubes are very good at providing fast answers to the queries that sort of business analysis type queries that I mentioned. So how best can we store that? Bearing in mind that this is the old diagram. Oh well. Bearing in mind that a data cube to most folks in the data warehousing world is actually this entire structure here. It's not the 3-dimensional cube that I just showed you. So this entire lattice is actually the data cube. For the purposes of today's talk, though, when I talk about a cube, I'm referring to one member of this lattice. So for the previous example, A, B, and C would be the dimensions, time, car or model, and the dealer. Okay. Other researchers would call this particular element perhaps a cuboid or a subcube. Okay, so data cubes are very large, take up a lot of space. The other thing that we know when we have large data is that there is probably some interesting information to be gleaned from it. Data mining has come a long way over the last few years with the increasing storage or accumulation of lots of data. Our researchers have tried to find interesting pieces of knowledge from that data. And a couple of the automated discovery methods, association rules is well established as a data mining technique. And the idea there is that you try and group together items that appear frequently in a data set. So, for example, if we're looking at market basket data, if I went shopping for a loaf of bread, what is the probability that I would also want a pint of milk and something else? So the association rules tries to pull out rules like that if we buy bread, then we will buy milk. The skyline operator is a different kind of automated discovery of information. It looks at data points, and for a point to be in the skyline, it must be as good as all the other points around it, but better than at least, and best in at least one dimension than the other data points. So these two methods try to find information from data automatically. And something we need to be a little careful of when we're finding automatic data, I have an illustration of here. I found this really rather neat graph. It shows President Bush's popularity rating. So the pink line is President Bush's popularity rating over the period 2001 to 2006, I think that is. Not very easy to see. And the blue line is the price of gasoline in the United States. So as we can see, when Bush was popular, the price of gasoline was low. And as the price of gasoline rose, his popularity declined. And, hey, who knows? Those things may be related. There may be a cause and effect there, but likely, more than likely, the war in Iraq had something to do with both of those two graphs appearing like that, right? But maybe not. Without expert domain knowledge, we can't say whether there's a causal relationship there or not. So another approach for finding interesting information in large data is OLAP, which is purely user-driven. The user submits a query, like that one that I gave you of the marketing campaign, and the OLAP engine will return to us a data set as a result. Well, that's good too, except that if we don't know what questions to ask, then we don't know how to get the interesting information from our data. So the obvious solution is to make some kind of hybrid of these two, to have some kind of automated discovery coupled with domain knowledge or user controlled or user guided questioning or querying. Okay, so we need to talk about some typical OLAP operators. These are in established OLAP software right now. A slice is to hold a value in one dimension constant. So this is Harry's slice of information. We've essentially reduced the dimensionality of this three-dimensional cube that we had to now 2 dimensions. So a slice tends to reduce dimensionality. A dice, the way we refer to dice in our work, means to hold values in 1 or more dimensions constant. We don't reduce dimensionality, we just extract a subset of the data. So here our dice is actually over Camry, the dates here, and the 2 dealers. Other researchers don't necessarily agree with those or use slightly different definitions for those terms. And the other OLAP operator that's important to the discussion today is roll-up. I may not care when sales were made. I may not care who sold them. But I may be interested in the total sales of a particular vehicle model. And we can roll up the information so we can sum sort of, again, we're reducing the dimensionality, and now we're reducing it, in this particular example, to a single dimension over models. Okay, so those are our typical OLAP operators that are well established. I'd like to now present our proposed operator, diamond dice. So for a diamond dice, we require that each and every attribute is used at least k times. And I'll come back to how we decide what k is and how we find out what k is. Essentially what we're trying to do is find a dense region within this vast, sparse data set that is the data cube. To continue the diamond analogy, we define a caret to be the count of the occupied cells in the slice. And the diamond cube is the maximal subcube with at least k carets in every slice. So there is a single diamond cube, and it is maximal. Yes, and every slice within that cube will have at least k carets. Some slices may have more. And we define the union of 2 subcubes as the union of their set of attribute values on each dimension. The usual set union definition here. We also, what isn't stated there specifically, explicitly is that it's the union of the set of attributes together with their associated measure value. So the union of A and B is B if and only if A is a subset or equal to B. So we've established some properties with respect to this diamond cube that does exist. So if we have a member of the daily cube lattice, like I said, a single one of those cubes, and a value of k greater than or equal to 0, there is a unique diamond cube. There is only one. And the proof of that follows from the fact that the union of two diamond cubes is a diamond cube. And another property that is important to the discussion a little later on, especially, is the fact that diamond cubes are nested. So our lemma says that the union of two diamond cubes, of two subcubes having at least k carats, has at least k carats. So the idea here is that diamond cubes are nested. If I have a diamond cube that has 5 carats, say, then the diamond cube that contains 6 carats is nested within that 5 carat diamond cube. And the proof follows from the lemma and from the union of union property of diamond cubes. And like I said, that's important for later on when we try and find k, because we know that diamonds exist, but we don't know from the beginning what k is. So our experimental data that we used was the Tweed data set. It was gathered together by a researcher from Norway. He was doing some social research. And there are 11,000 records in it. Not a large data set by data warehousing standards, but it is a real data set, and it was interesting for our initial experiments. It has records of acts of internal terrorism that occurred, or domestic terrorism that occurred between 1950 and 2004. So it records events like IRA bombings in the United Kingdom or ETA kidnappings in Spain, that kind of thing. So all the acts of terrorism happened domestically, they weren't international. The data set itself has 52 dimensions, including action, so what happened, whether it was a firebomb, whether it was a letter bomb, whether it was a kidnapping. The target, so who this action was aimed against, whether it was the public or the police, how many people were killed on both sides, how many people were injured on both sides, etc., etc. So we took this data set and we did some pre-processing. Well, we did a couple of things. First of all, we rolled up the data to remove some of the dimensions that had obvious dependencies. If the terrorist agent was a Catalan activist, then he obviously was going to be doing something in Spain. So why include both attributes in our set? So we rolled it up to reduce the amount of dimensions. So the initial implementation created a bitmap of the entire data. So this is a two-dimensional cube, country and action, and each of our allocated cells that are colored blue here would correspond to an action and a country. So here we perhaps have the United Kingdom with a firebomb. Here would be the United Kingdom with some other action. Here might be another country with a different action. Okay, so we create this bitmap, and then we process this bitmap. So the bitmap becomes the feed into our initial algorithm. And so we feed in the bitmap, and we feed in a value of k, and we process the dimensions one by one and prune away all the dimensions that, all the attributes that have less than k values allocated. Rather than sort of step through the pseudocode, it's probably easier to see what's going on here with an example. So I have an animation of the algorithm. Here, k is 3. and that should be noted on there. I apologize for missing it. So K is 3 in this example, and I have some actions and I have some years. And what the algorithm, yes?
Question. It's a bitmap, so it's 0, 1 there?
Yes.
Okay.
Yes. Yes. We for now it's just 0, 1. We can eventually include measures, and we will do. That's sort of part of the further work. Yeah. So the algorithm will process dimension by dimension. So if we process this dimension first, we check to see how many attributes here. Well, we have more than 3, so that remains. We have 3. That one remains. We have more than 3. Failed only has 2 attributes, so that gets pruned out. We continue down, and car bomb has 3, so we're okay. We've processed this dimension. We have to now process the other dimension, and 1984 is okay. 1985 is okay. 1986 needs to be pruned out. 1987 is okay. 1988 is okay. Because we made changes in this last iteration, we have to go back and reprocess our first dimension again. And when we reprocess our first dimension again, now we lose arson because it's now down to less than 3, which is down here. And this one's 3, this one's 3, this one's 3, we're okay. And we have to, again, process our year dimension. So we now lose 1985. And if we run through this one more time, we'll find that we're stable. We won't make any changes because each of these attributes now has 3 allocated cells. And there we have our diamond cube. Now, that is a perfect diamond. Every cell is allocated. That is very unlikely to be the case in real data. But for the purposes of the example, it works and shows you how the algorithm, the initial algorithm works. So we implemented this on an AMD Turion 64 with a 2 gigahertz processor with 2 gig of RAM. And the software, we started out, the first implementation used multidimensional arrays. And we found that they processed so slowly that it really wasn't worthwhile continuing with it. The multidimensional arrays were storing all the zeros, like all the empty space, and we were processing all the empty space, so it took a long time. In fact, some of our runs never did complete. So we changed the data structure that we're using to a multi-linked list. So now instead of arrays storing where all these allocated cells are, we have multiply linked lists. And that works much, much more efficiently. And back to K. Remember I said earlier on, we don't know what K is when we're presented with the data set. We have to find it. So we have a couple of ways of finding it. Our first approach was to say, okay, K is 1. Try and create the diamond. If we create the diamond, then let's try K of 2 and keep going until we can no longer increase K. And because diamond cubes are nested, we can do that reusing the same structure that we built the K1 diamond from to look for the K2 diamond. And the other approach that we took is that we know the maximum value that K can possibly take. And based on that, we can do a binary search over the range of where K would be legal. So we can try the midpoint, and if we're successful in building a diamond at the midpoint, then we can try the further midpoint in the higher part of the range. So, like I said, we didn't retain all 52 dimensions. We built 7 different cubes, and we retained different combinations of what seemed like the most interesting dimensions. And as you'll see from this, our 4-dimensional cube was the least dense or the sparsest. It had the fewest allocated cells. And for each of these cubes, we generated the diamond cube. And here's a comparison between the execution times of the two different implementations, searching for K sequentially and searching for K using the binary approach. And in every instance, in this particular data set, in every instance, our binary approach was more efficient. In fact, for item number 5, for cube 5 here, it was extremely efficient. And there's a reason for that. The maximum value that K could take in this example is 11. It can't be any more than 11. And the value it actually takes is 8. Well, if we do a binary search over 11, we hit 6, we hit 8, we're done. We only have to look twice to find it. And there's a couple of charts about showing the original density of the data and the density of the diamond cube. And in every case, we've increased the density. And notice that cube number 1, which was our 4-dimensional cube, which was the one that started out with the least density, benefited the most by this diamond dicing operation. So that leads us to hope and believe that our operator will be really beneficial in high-dimensional data sets. And what else? So, to summarize, our diamond dice operation does increase the density without reducing dimensionality, and our linked list implementation returns a diamond cube. Those are facts, and we have some other things that we want to investigate with respect to this. The first one, obviously, is large data. That 11,000 records for the tweet data set was very small, so we need to execute this on large data. We've done some work on synthetically generated large data, but we're going to continue working on a real large data set. We want to look at independence. We have a conjecture that if there's a correlation between the dimensions, then we would generate a large, sparse diamond cube. And we want to look at that by generating data that we know is correlated and testing that conjecture. We've looked at the diamond itself. We haven't looked at the complement. So the complement would be all those elements that were pruned away. And there could be some interesting properties associated with it. Updating this structure, we need to decide whether or not creating an update algorithm is going to be useful. It could very well be that it would be cheaper to build the entire thing from scratch. Most of these data warehousing, data cubes and things are generated offline at times when the data is not being used, and sort of the pre-computed and then used later. And it might very well be that our diamond cube is going to have to be used in that way rather than having it as a structure that gets updated as the underlying data gets updated. We've looked at right now our structure depends on the count of attributes, and in real data sets, often the cardinality of the dimension, so how many attributes in each dimension, varies considerably. We could have a dimension that just has a binary value, gender, male, female. And then we could have another dimension that had maybe thousands of different attributes. So it might be a good idea, and it's something that we don't plan to investigate, as a fractional diamond, one where a given fraction of the available cells are actually occupied, rather than a base count of cells are occupied. Sum-based, obviously, we need to look at other operators or other aggregators like sums, because right now it's just really based on existence of a relationship, not how influential that relationship is. And finally, we need to look at the diamond in the context of the lattice and its interaction with other operators, in particular the iceberg cube. Yeah, so I think
It's okay.
I'd be happy to take questions. Thank you.
Maybe you have some questions for Hazel?
So I think I got the most of it, but the important thing I didn't understand is why exactly we're looking for diamond cubes.
Why are we looking for diamond cubes? Well, in the business sense, a question might be what combination of attributes together, or what combination of things together provided good sales for us in the last month. So not just what sold well, not just whether we sold tables, and but the number of tables that were sold, the number of products that were sold, coupled with the people that sold them at the same time. So it's sort of a query that would look at how things combined to make good results for us.
I could probably comment on this as well. There's a lot of people have, for various good reasons, be it storage, indexing, and so on, have been looking to find dense subsets in data cubes. And why do you care about dense subsets? Well, okay, so you're a web social guy, so let's take Facebook, okay? And so you might want to look for a clique, a large set of all mutually connected people. And then you say, okay, I want to have the largest clique I can find on Facebook. But that might be the query you would want to ask, except that that's NPR'd. Okay. I mean, whenever you ask for the densest sub-regions and so on, it does tend to turn into something that's NPR'd. There are exceptions like concepts, for example, that Robert works with.
Well, when you have constraints, you can have problems that are not as
hard.
But without constraints, it's going to be.
It does tend to be, and certainly in OLAP, there's no. I'm not aware of any good definition that's both workable, that is, computationally you can process it, and at the same time it does provide something that is dense in some sense. So one thing we've shown recently, for example, is that in a sufficiently high-dimensional cube, the minute you have a subregion that has some density, and does not need to be very dense, just a little bit dense, it will contain a diamond.
Okay.
So we cannot really compute this really dense subregion, but in some sense, diamond is somewhat of an approximation, because if you do have a dense subregion, then it will contain a diamond. And there's a very fun proof about this. If you give me something that's fairly dense, then I can just start taking it apart and say, okay, if it does not contain a diamond, then it must have at least one slice that has fewer than k-1 elements, and that is k-1 or less elements. And then you take it out, and you know that what remains must not contain a diamond, and so you can keep taking out slices. And when you're done, you realize that you haven't taken out that many allocated cells. So what you started with cannot be that dense. I mean, you need to see the math, but so it's essentially a practical definition of density. There could be others, but I mean, someone has to propose a density measure, and that's one that's a workable one, I think.
You want to go to
No, that's.
I have, yeah. Do we have some time? Yeah. There's some I missed some links there. When you're looking for a diamond, do you fix the K parameter?
When we're actually looking for it, we do. The theory says that we know K up front, but actually we don't know K up front. So what we do is, in this example,
Okay. So,
if we were to actually process this from the very beginning, we would process it from the point of view, of saying, let's begin with K at 1. The maximum value K could take here is 5, because we have 5 elements in this. 2, 4, 5, yeah. Well, we have 5. We have a 5 by 5. So the maximum it could be is 5. So one approach is to say, okay, let's try it at 1, see what happens. Let's try it at 2, see what happens. And
does your algorithm do that? Or?
Our implementation does. The algorithm that I put there and described assumes that we know what K is originally. Okay, so.
But I don't know.
You mean the maximum value?
Yeah, another way to
for
spin
which-
it is that you're looking for the maximum value of K, for which
For
you
which
don't have
there's-
something
there's-
empty.
There's a K.
Yes, yeah.
But does your algorithm do that? Or you say, I know in advance it's 3, and then it does it?
What we do is we pass the parameter K, and first time around, if we were doing it sequentially, we'd pass it 1.
Then 2.
And then 2, then 3, until we get an empty set, and then
And do you
then we know we've
use
gone 1
the
too
result of the previous
Yes, you can.
thing to refine your search
Yes,
there?
yes, you do. We use the same structure. As long as the value of K is increasing, we can do that. If we were using binary search and we guessed the midpoint and there was no diamond, we would have to start from scratch and build our new structure over again, because we would have destroyed all the information, finding that there wasn't a K at that, or wasn't a diamond at that level of K. So we can reuse it as we can reuse the structure that we build as long as K increases.
Because the thing that, the analogy I see, simple analogy is with all the work on frequent sets.
Mm-hmm.
And I was wondering if you use some of the techniques that are known to be useful in frequent sets in your processing there, or is it completely unrelated?
It's largely different than the frequent sets. I think there is one implementation of frequent item sets that does use a bitmap as part of its pre-processing. So from that aspect, this implementation I described today is somewhat similar to that one. But other than that, there is not a lot of similarity between us and frequent item sets, no.
Okay. And things like co-clustering.
That's something that I have to look at. Certainly, yes, in the biomedical field, bi-clustering is
Because you have related subsets of things.
exactly, and you know, in 2 dimensions, that's really what we're generating. Ours
In 3 so there it's you have to generalize to something there.
That's right. Yeah. So ours generalizes beyond.
It would be interesting to see the links there.
Yeah.
Something.
So I think actually in your work, a perfect diamond would be the equivalent of your Galois lattice with that center, the center guy filled, right? So but only for the perfect diamond. Outside of that, we kind of diverge.
So you say that's a perfect one.
Yes, all the cells. This one here, because all the cells are allocated. But we could.
What I'm missing is that what would be an unperfect diamond?
What would be an imperfect diamond? Okay, it would be one where all of these guys had 3, and maybe 1984 had 4.
Oh, you have more than 3.
That would have more than 3. That's right. Yeah, and maybe there was Actually, maybe if we, yeah, then we'd have to have another row here that would have 3.
Because what happens, the reason why this won't, because we're stuck on a 2D display here.
Yeah.
But think about when you're working in 10 dimensions, right? And here you have an example of a 3-car cube, and so it's okay. But then project this in 10 dimension. Then how many allocated cells would you have? You would have 3 to the 10. It would be a lot, right? So the perfect cubes like this don't exist. That's why you cannot really do concepts the way you do in 10 dimensions, because then you'd have, in 10 dimensions, something that's perfectly dense is...
People have worked on 3.
but it gets totally crazy, right? Well, yeah, but at 10 or 20 dimensions, it's like all the math is gone. And in this case, then that's why this is not really a typical case in high-dimensional spaces. So imagine one. Yeah, you could have something 4 by 4. You don't have the example here. Well, the good example is that.
Actually, if we take the first one.
Yeah, the first one is a 2-carat.
A 2-carat.
You have 2-carat. That's an example of the 2-carat.
Yeah.
Because you have at least 2 allocated cells per slice.
Okay. But you may have more, and that's why.
Yes. Yeah.
So you take more of the other cells into account in your density measurement.
It's less expensive.
Pardon?
Celui-là, il est pas cher. It's less expensive.
Non, les diamants, les carats.
So is there an assumption that the maximum K is the most useful diamond? If you can find smaller diamonds with smaller K?
That's a really good question.
Yeah.
It might be true that it's the most useful. If we think about somebody looking for the densest area and limiting the number of rows that they want returned, then we can't. The diamond is not guaranteed to be in that set, but it certainly could be a very good place to start looking for a dense area with some kind of limited number of rows returned. So it may not be the best or the most useful, but it could be very useful in helping find dense data sets. Plus, some of the experiments that we've done has shown that although the diamond doesn't have to be in the densest subset, it very often is.
But you always have one.
Yes.
Okay. But I would imagine the idea of having overlapping subsets of things which are interesting.
Which is where I think work on the complement is going to come in, because I think there was one paper I read quite recently where the researchers were searching for a set of dense areas.
Yeah.
And I took their example and applied our diamond dicing to it and got their densest region. But then when I took the complement, so the values that we had thrown away, and applied our diamond dice to that, I got their next most dense area from that. So I really think that...
This is often the kind of approach used in clustering.
Yeah.
Greedy clustering.
Yeah. So I think, looking at the complement, I think, is going to be interesting.
But then you can't have overlaps.
That's right. Yeah, we wouldn't have overlaps, but...
I'm wondering about the resolution. For instance, you have years down here, and obviously we could collapse sets of 2 years together to have a reduced. You have the same number of dimensions, but you have less resolution on the.
Okay, yeah.
Or you could have something that's so fine-grained that it causes other problems. I'm wondering if you thought about this or how it did.
That's coming back to this guy here. I should jump to directly. Where to go? There. This is somewhat similar to what you're talking about. You know, the information here is much coarser than the information down here where we've got all four dimensions shown. You're talking about within the dimension, right? Collapsing sort of attributes within a dimension. This is collapsing dimensions, but it's a similar idea. And yeah, that's certainly one of the things that we have to look at.
Going through hierarchies in the values.
Yes, yeah.
Can you explain that picture? Because
Explain this picture,
it looks like pointers, and it looks like the actual data points are at the top, but I'm
Oh, okay.
confused.
So, yeah, this would be a four-dimensional cube.
Okay.
So A, B, C, and D are the dimensions. And if we talk about our car sales example, then A might be the time, the date. B might be the vehicle model. C might be the dealer. And D could be color, for want of a better dimension. Okay, so in here we have the data stored at that level of granularity. So we have the sum of sales for every day, for every dealer, for every vehicle, for every color, stored separately as cells. Up here, we don't worry about color. So now we've collapsed color, and all we're interested in are the day that the vehicle was sold, the vehicle, and the dealer who sold it. So if Bob sold a red car and a blue car on the same day, it doesn't matter. The sum of those sales are pulled together. Okay. And likewise, going all the way up to here, where all we're interested in is the sales per day over the year. And this one would be sales per vehicle over the year, no matter who sold them, no matter what color they were. Okay?
So you can build all of it from what is at the level 0, right?
Yes. Yeah.
But so the idea of a lattice like this is that if you're only interested in two dimensions, then you're better off working, picking up the right cuboid and working with that instead of the large one at the bottom, which will involve a lot more data.
Okay, it's like pre-collapse.
Yeah,
Yes.
it's like pre-collapse.
Yes. Yeah, exactly.
But imagine if you had 10 dimensions, then this thing would be like huge. Right. You'd have 2 to the 10 blades.
Visualizing in 10 dimensions. Hard.
It's hard, eh? It's hard. Yeah. And the other thing too is because these problems grow so quickly. Right now, our implementation is an in-memory implementation, but we are finding very quickly that we're going to have to develop some external memory algorithms to handle this because
very large.
Yes. Yeah.
Do you have a question for Hazel?
That's great. Well, thank you very much.
Okay. And good luck for the training.
I didn't understand. Who is your director?
Daniel.
I said Daniel. You didn't tell me that.
You got two directors or one? Good choice.
Yeah.
Oh, yeah.
Dr. Kaiser too.
Precies
UMB
nog
St. John.
veel,